Hello everyone, let's solve GATE paper CS1 question 44. Consider the following two languages over the alphabet A, B, where L1 is A alpha, beta, alpha, or alpha belongs to A, B plus and beta belongs to A, B plus. L2 is alpha, beta, alpha over alpha belongs to A plus and beta belongs to AB plus. Which one of the following statement is correct? Let's understand the prerequisites first, and then we will try to solve this particular question. So, let's first understand what is a regular language. A regular language is one such language in which that can be recognized by finite automation or expressed by regular expression. A regular language cannot match the same string in two non-adjacent parts. It it cannot count arbitrary amount of like matching number of A's in two different places. It cannot handle general practices or patterns like WW. These patterns, let me write that. So the patterns like WW or W to the power R or alpha, beta, alpha, if alpha belongs to A, B plus. It cannot handle journal patterns like these. It cannot match the same string in two non-adjacent parts. It cannot count arbitrary amounts, like matching number of A's in two places. It is recognized by finite automation and expressed by regular expression. Pumping lemma. What is pumping lemma? It is used to prove whether the language is regular or not. If a language is regular, then there exists a number p, which is a pumping length, such that any string with modulus of s greater than equal to p can be split into x, y, z, satisfying. Let me write that. So, if a language L is regular, then there exists a number p. P is belongs to pumping length such that s belongs to that language and modulus of s is greater than equal to p, like length in positive, obviously, and it can be split into x, y, z such that we can split. So a string s uh, can be split down into some x, y, z, some sort of that, such that modulus of xy will be less than equal to p, mod of y is greater than equal to 1, and I is greater than equal to 0, and x, y to the power I, z belongs to L. If we can find a string in a language that cannot be pumped, then the language is not regular. So, in short, the language is regular if there exists a length p um, such that any string s belongs to that language and that length of the s is greater than equal to p can be split into xyz satisfying these conditions. Otherwise, if we cannot find, if a string cannot be pumped, it is not regular. Let's understand the alphabet notations basically. So the one A comma B plus, which I was writing continuously, that is basically non-empty strings. Non-empty strings over A and B. Alpha and beta are strings. Alpha, beta, alpha means same prefix and suffix. I hope this is clear. Now, let's understand some language definitions. So, L1 is given as alpha, beta, alpha, that means same prefix and same suffix. Alpha belongs to strings over A comma B, and beta belongs to, like beta string belongs to strings over A comma B. Yes. Alpha can be any non-empty string over A and B. Beta can be any non-empty string over A and B. Requirement is the requirement. This is the requirement basically. The prefix and suffix must be identical. So it is not regular. Can you tell why? Can you think of anything? Basically, as I said, which patterns it cannot match? WW, W to the power K, and alpha, beta, alpha. Finite automata cannot remember an arbitrary string alpha and ensure it is repeated later. Okay, that has been told. This is similar to the language WW, like AB, something, which is not regular. So L1 is not regular. Okay, language L2. Let's understand that. So L2 is equal to alpha, beta, alpha, where this is a requirement where alpha belongs to over A plus and beta belongs to AB plus. Now, alpha is only made of A, like A, like multiple A's can be there, but still, structure of some A's and then B and then some A's. So the structure, like these kind of structures can be there. This is AA and then B and then AA like this. So it is somewhat like equal number of A's before and after the beta string, any random arbitrary beta string. So it looks somewhat like this. Language 2 belongs to alpha n, beta alpha n, where this is n greater than equal to 1 and beta belongs to, not like alpha has been replaced with A. Okay. Beta belongs to AB plus. Let's look a bit deeper. Let's rewrite this a bit. It indeed look non-regular initially, but let's go a bit deep and understand what it is. So L2 is A to the power n, beta, any random beta string, A to the power n is greater than equal to 1, and beta belongs to AB plus, a string over A and B. Okay. So looks like we need to match equal number of A's before and after, because value of n will be same both in prefix and suffix. If beta were empty, then it will become, if let's say beta is empty, for example, first case empty area, then it will become A to the power n empty A to the power n. So A to the power n, A to the power n is equal to A to the power n plus n is equal to A to the power 2n minus like, okay. But beta must be non-empty, and it between two A blocks, we can construct a regex for this or a regular expression for this. Okay, beta must be non-empty and is between two different blocks of A's. Hence, we can construct a regular expression for this. Let's understand why this is actually regular, because indeed it looks irregular, but it is regular. Let's understand why. We assume alpha belongs to the string over A's and beta belongs to string over A and B's. So alpha is just a block of A's. So we can generate L2 with a regex expression like this. L2 will be n greater than equal to 1, A to the power n, A or B, something, plus A to the power n. We don't know like what it will be, either A or either B. It is a finite union for any fixed n, and finite unions of regular expressions are regular. Remember, it is a finite union. Remember that. Okay. And finite unions of regular expressions are regular. Okay, but more elegantly, if I go a bit more deep into this, then we can build a NFA, non-finite automaton. Read A's, basically whatever A's, and store A's using finite states. Some finite state we can use to store them. Then transition to a state where beta can be either A or either B, depending. Then read the same number of A's again. So first some number of A's, then some random A or B, then uh, so it regains like returning to the earlier path. The key insight is if we fix alpha over A and then we don't match the string content. Let's say I fix the alpha over A and then we don't match the string content, only match the fixed number is A's and start A's at the start and end. You can build a regular expression for such patterns up to a fixed bound. But here is a trick. Let's say A belongs to A plus and beta belongs to A or B plus. So language can become like this. A plus, then A or B plus, then A plus. Correct. This include some cases like this can be multiple A's. So it can be double A. It can be triple A on both ends. This is regular. This is regular because it does not require matching string content. Just some A's are there before and after. We don't need to match it. Regular expression can model some A's at start and end. So no need to ensure the same number of A's. Any non-empty A's before and after can suffice. So the key difference is L1, L2 prefix must exactly be the same arbitrary string, but L2 in language 2 basically, prefix and suffix are just non-empty A's because the alpha is just belonging to it. Like it is not having a polarity with other character. So it can be matched with regular expression. Hence, the final option which is correct here is option C. Which is L1 and L2 are regular. So it is not correct. L1 is regular language, but L2 is not a regular language. That is also incorrect. We just figured that out. L1 is not regular, but L2 is a regular language. Yes. And neither L1 and neither, that's not the case. We already figured out that L1 is a not a regular language and L2 is a regular language. Okay. I hope this is clear. Now, this finite automation, what is that? Some people might ask, what is finite automation? So, finite automation is a theoretical machine that used to recognize regular languages. It is called finite because it has limited number of states, finite number of states. There are two types, deterministic and non-deterministic. So, structure of a finite language can be done in five different tuples. Set of five tuple basically. If you guys don't know, this is a bit of theory which we are covering because it is needed. Q, Q naught, and S. Where Q is finite number of states, finite states. This is sigma, which is input alphabet. It is delta, which is transition function. Like Q into sigma is equal to Q, whatever it is, you can say. Like it is a transition function, and Q naught is the initial state, and F is the set of accepting final states. Okay. So we can like five tuple we need to figure out. Like it basically starts at initial state, read the input or one symbol at a time. It uses transition function and to move between states based on the input. And after reading the entire string, if it is an accepted state, then the string is accepted. Otherwise, it is rejected. DFA for a regular language is remember that it is basically a to the power n, b to the power m, where n is greater than equal to 1 and m is greater than equal to 1. This is a DFA to accept a language. Okay. Now, what states can be there? So Q naught at least start, except at least one A. Q1 is basically at least one A and except one more A or transition to B. Q2 can be at least one B and except more one B, and Q3 can be a trap state, invalid in. So different state. Q naught is basically accept at least one A. Uh, and Q1 will be at least one A and can accept more A's or transition into B's. Q2 is at least one B and then accept more B's, and Q3 is a trap state. So transition looks somewhat like this. Q naught, A, Q1, Q1, A, Q1, or like Q1 to B to Q2, or Q2 to B to Q2. Okay. Accepting Q2. Hence, it ensure that there are at least one A's and at least one B, because A to the power n, B to the power m, n or m both are positive. So at least one A and at least one B. The automation cannot remember arbitrary number of things like a stack or a counter. Hence, these kinds of patterns are prohibited when there is a parity of like character. Example, it cannot match equal number of A's and B's. It cannot ensure whether the string is palindrome. Hence, not regular. So if you recall that alpha, where alpha belongs to a comma b plus and beta belongs to a comma b plus, it is not regular because you need to compare two arbitrary substrings and it requires memory, and it is not possible with finite states. Where L2 is alpha, where alpha belongs to a only, because prefix and suffix are just a's. We don't need to remember how many a's. It can be just a's. A finite automation can match any number of a's at start and end, provided they are just a's. Okay. We can design an NFA that read A at start, goes into some state in the middle, and then ensure the final part is A only. Hence, it can recognize finite part, like can be recognized on regular languages. Okay, that's it for this particular video. Take care. Bye bye. Just for the answer, L1 was not regular and L2 is regular. Option C. Take care. Bye bye. See you guys in the next video.